thank you. So first of all, thank you very much for giving me this opportunity. And thanks to the audience as well for staying until the very last talk of this session after such a long day. I'm going to talk about electroweak MSSM under scrutiny as mentioned in the title, but now I think that I should add a few words. Electroweak MSSM under scrutiny again, and an optimist approach maybe to set target for future colliders. And this talk is based on some of my recent works that I've done with my collaborators, Monimala Chakraborty, she is a postdoc in Warsaw, and Professor Sven Heinemeier and Professor Christian Schaffer. Okay, so this has already been shown in previous lectures that the current status report given by the Atlas SUSE researches, and it shows that currently LHC has it has increased limits on the particle masses. In particular, if we look closely, that even now the limits on the particles at the electroweak sector, it has relatively moderate limits than the limits on the strong sectors, which has already reached almost around 2 TeV. So these limits are still within 1 TeV, as we can see from these latest their summary reports given after the 13 TeV run. Now, of course, I don't have to talk much about the model in front of this audience, but just a sake of completeness. So the MSSM has ample particles in the electroweak sector consisting of Higgsinos, Winos, Charginos, and Sleptons. And the neutralino, so after the mass diagonalization, of course, there are 4 neutralinos, and the masses are dependent on the Gaugino mass parameters U1 and SU2 and the Higgs mass parameter mu, while the charged Higgs and Winos mixes to give us 2 Charginos. And in these sectors, only the masses are dependent on the input parameters like the Gaugino parameters M1, M2 and Higgs parameters, and then there is these tangent beta values. Now, if we are considering the R parity conserving scenarios, then of course the lightest neutralino can be a viable WIMP dark matter candidate, and it has been a most favorable candidate for long. In the Slepton sector, we have Sleptons for 3 generations, and the masses depends on the input mass parameter for the Sleptons in the for both left or right cases. So in addition to the electroweak Gaugino input parameters, there will be 2 additional parameters that will define the all the masses of the neutralinos, Sleptons, and the Charginos. Okay, now talking about the current constraint on electroweak MSSM, of course, since we are going to scrutinize the parameter space, we should understand what constraints are currently imposed in this sector. So starting from the LHC searches, so in particular in the electroweak sector, we have seen that from 13 TeV and after the final run with the highest luminosity 139 fem/1 inverse, this is the limits that has been given by the Atlas collaboration, and they have done various search, they have looked for various signals for the production of both the Sleptons as well as the Charginos or the associated production of the Chargino 1 with neutralino 2. And we see that depending on the various decay modes of these Charginos and neutralinos, the mass limits is varied. And here also we see that depending on the flavor of the Sleptons, whether it's a 3rd generation Staus or first 2 generations electrons or muons, the mass limit varies. However, as I already mentioned, that the limits is still moderate because of the modest production cross section at the electroweak sector, and so the LHC limit is comparably weaker than what we have for quarks or for gluinos. The interesting part for electroweak MSSM is that it may also show up elsewhere in indirect searches. For example, since if the in the arpetic conserving scenario, if the lightest neutralino is a dark matter, then dark matter searches could also give us additional constraint on this kind of model. And then there is one recent very interesting results that came up for the mu1 G-2 searches from the Fermilab run one data. Just to summarize again the relevant searches at the LHC, we have just redrawn the mass limits and discussed what are the assumption that has been taken by the experimental collaborations to draw the limits. For example, in this red shaded region, they are considering the production of chargino 1 with a neutralino 2, and those decays to lepton and neutralino via leptons. However, in this kind of searches, they have always considered the simplified assumptions, where they considered that this kind of decay modes for the charginos or neutralino 2 is 100%. And also the gaugino composition of the neutralino is pure Bino. The same thing is done for other search modes. For example, here they considered 100% decay branching ratio for the charginos and neutralinos decay via on-shell gauge bosons. And one very interesting search prospect is the compressed spectra searches, where they look for very compressed spectra between charginos and neutralinos, and then the decay is happen via the off-shell gauge bosons. So they required some kind of initial state radiation to derive the limit on this mass scale. Similarly, for leptons, they considered 100% branching ratio of leptons to lepton and neutralino, and then also the compressed spectra searches, where these are where they consider the off-shell decay modes. Now, from the dark matter point of view, so since the neutralinos has to give a right amount of relic density observed by the cosmological evidences, we can have several annihilation channels, but depending on the gaugino compositions and the mass gap between the other particles, there could be co-annihilation mode. And it has been well studied that if the neutralino is a Bino-Bino or a Bino-Higgsino kind of LSP, then a chargino co-annihilation can give rise to the right amount of relic abundance. While if it is a pure Bino type LSP, then lepton co-annihilation can yield the right amount of relic abundance. While this kind of neutralino dark matter will contribute both to spin independent and spin dependent contribution to dark matter direct detection. Finally, the recent result that has rekindled the study of electroweak MSSM is the mu1 G-2. And there was a long-standing discrepancy between the standard model value with the experimental value of Brookhaven National Laboratory result. And after many years, the Fermilab collaboration, G-2 collaboration, has released their result for their first run last year. And the current experimental average shows a tantalizing 4.2 sigma discrepancy with the standard model. Of course, there are some debate on the lattice case theory results, but in this theoretical average, the lattice result has not been included. And it shows that we are in need of some new physics that can explain the discrepancy between the theoretical and experimental result. And none other than the electroweak sector of MSSM can be a good candidate that can easily explain such discrepancy. And we see that that can happen because of the chiral enhancement. And if we consider the mass insertion approximation, we see that the chargino neutrino or like Bino-Higgsino kind of mixing or Bino-Higgsino kind of mixing can give rise to additional contribution over the standard model prediction for the mu1 G-2. And since both of these contribution is of course proportional to the tangent beta, Therefore, for a large tangent beta, we can get an upper limit on the mass of this kind of supersymmetric particle from the bound of the experimental values on the G-2. Based on this, we subdivided or categorized the parameters of the electroweak MSSM based on the nature of the dark matter. And then again, if we consider that either the neutralino dark matter can explain or can give exactly the current abundance needed to get the right relic abundance for the dark matter of the universe, or at most it can give or it can contribute to a fraction of the total abundance of the dark matter in the universe. Based on this, the dark matter can be of either of these kind of 5 gaugino natures. So either it's a Bino-Vino or a Bino dominated dark matter, or it can be a Higgsino dominated or a Vino dominated. However, if we take the mu1 G minus result seriously, then since mu1 G minus 2 has will already put an upper limit on the neutralino mass as well, therefore we cannot get the correct abundance for the pure Higgsino or pure Vino case, because that requires much larger neutralino mass, which will not satisfy the mu1 G minus 2 result. So based on this classification, what we have done, we have tried to study the spectrum of the electroweak MSSM, and the experimental observations that we have taken into account are the mu1 G minus 2 at 2 sigma, and then the correct or low relic abundance, and then of course there is the direct detection bound from xenon quantum. Along this, the LHC constraint, the current LHC constraint must also be taken into consideration, and that demands an recasting of the experimental analysis. Why? Because as I already mentioned, that in the experimental limits given by the experimental collaboration, they have considered specific gaugino compositions for the neutralinos or charginos, and also specific branching ratios. So in practice, in a particular model, we should consider all possible decay modes, and then we see that if the current data gives the exact limit that has been given by the experimental collaboration. And for that, we have considered a publicly available code, checkmate, that was also mentioned by Nishita. And in that code, what we can do, we can use use any new kind of model, and we analyze the particular signal for any new kind of model, and then compare the signal event for a particular analysis and a particular signal channel with the signal event that is given by our experimental collaborations. And then from a statistical evaluation, we can compare with the number of signal events that can be obtained in our particular model, in any BSM models, not only in the MSSM, and then we see if that violates the limits from the experiments. So we have implemented these models via checkmate, and I will show that proper recasting is interesting, and maybe we are in need when we give the limits, or when we show the limits for particular BSM model, maybe we should consider of doing this kind of recasting instead of just following the limits given by the experimentalist. So to start with, I show the chargino-lepton co-annihilation scenario, where we have considered that the neutralino is giving us the correct relic abundance, and here it can be chargino or lepton co-annihilation, sorry. So in the left side, I was showing the Bino-Vino co-annihilation scenario, where M1 is so this is my range of parameters that has been scanned. And here we are considering an universal input mass parameter for the leptons, and we are focused in the Bino kind of small mass gap between Bino and Vino. So we scan the M2 within 10% range of M1, and we see that these green points, these are the allowed points by the G-2 current G-2 result, at 2 sigma range. And we can clearly see that the upper limit on the charginos, on the neutralinos and charginos, is around 700 GeV. While the upper limit on this kind of on these models, on these particles come from G-2, there will be a lower limit on this kind of masses that will be given by the LHC searches. But of course, since this is a chargino co-annihilation scenario and the mass gap between chargino and neutralino is very small, so only the compressed spectra searches is important. And here we see that masses below around 150 GeV is excluded, clearly excluded by LHC compressed spectra searches. On the right hand side, the similar exercise has been done, but for the lepton co-annihilation case. So here the neutralino is kind of BNO dominated, and it co-annihilate with a light left kind of leptons. So ML is near within 20% of M1. However, we varied the right lepton mass, unlike the previous cases, independently. And here also we see the upper limit from the mu1 G-2 is almost similar. So in this case, while the charginos neutrino diagram contribute largely to the G-2, enhanced G-2, in the left slide, the lepton diagram will be important. Here also there will be lower limit from LHC searches, and compressed lepton searches is important in this kind of scenario. However, since the other masses, for example, in case of chargino co-annihilation, the leptons are independent. Lepton mass can be heavier, much heavier than the neutralinos, and the mass gap can be large. So lepton searches will be important in this kind of scenarios. But we see that, I'm sorry, this is chargino. Sorry, this is for leptons. I think I switched the plot, sorry about that. So this is for lepton co-annihilation, where the chargino masses can be large. The mass gap between charginos and neutralinos can be large. Now, interestingly, we see that this black solid line is the limit given by Atlas 13 TeV result, and particularly from charginos and chargino 1 and neutralino 2 decaying via leptons and giving rise to 3 lepton plus missing energy signal. However, as we can see that the branching ratio to that particular decay mode can be significantly reduced if there are additional branching ratios of charginos via staus. So so proper recasting can still allow chargino masses within 1 TeV or so. However, G-2 has already carved a mass parameter from above. On the other hand, if we consider the chargino production, where the lepton masses can independently large and the mass gap can be larger, there also we see that the current bound from experiments is given by this black solid line, while if you consider the proper branching ratios and the Mangino composition, then even we can have viable parameter points inside this limit given by Atlas, because there can be considerable branching ratio for the leptons decaying via charginos, giving rise to less number of signal leptons at the detector and relaxing the limit coming from 2 lepton plus missing energy searches. How much time do I have? Okay. So this shows the importance of recasting the experimental limits. Now, what about the pure Higgsino or pure Wino case? Of course, in that case, the mu is the lightest parameter, and then only the mass gap between the NLSP and LSP, NLSP and LSP is delta M here, is much smaller than that we have found in previous chargino co-annihilation or lepton cases. So here also the NLSP is neutralino 2 or chargino 1, but the mass gap we see is around 10 GeV or so. Now, of course, here the direct detection of dark matter plays a crucial role, and that these blue points, these are discarded by the xenon quantum. At that time, xenon quantum was the latest bound. Now we have, of course, LZ latest limit, which has not been considered in this plot. So this they put upper limit on the mass gap, pushing the towards more pure Higgsino kind of scenario and allowing only small masses by direct detection. So these cyan points are all allowed by direct detection. And here only we are considering, of course, the upper limit from relic abundance. But the LHC compressed spectrum searches is also relevant here, and it sits exactly in the sensitive place for the LHC searches. But here also the Slepton searches can also be relevant, but I'm not showing that plot. So we see that if for future direct detection, it will push towards, again towards, if we didn't find anything for the null result, it will push again to small mass gap, and the compressed spectrum searches can again push towards the higher mass values of the NLSP. So this could be important for these scenarios. On the other hand, for the WINO case, the chargino and the neutralino mass gap is much smaller, even smaller than the Higgsino case. And here the relevant LHC search will be the disappearing track searches, because of the low mass gap, the charginos will decay via pions and give rise to disappearing track searches. And again, the direct detection limit, here again the blue points are discarded by the xenon quantum direct detection. So in the case of Higgsino and WINO, while we have a upper bound on the NLSP mass from G-2, this mass gap between the NLSP and LSP will be controlled by future direct detection as well as future collider constraint. So what are the targets for future collider? Here we try to show the limit on the cross section that we can achieve. Of course, it considers far future colliders such as CLIC 15,000 and ILC1 TeV. But we show that these points are the viable or the satisfied parameters point that satisfies all the current observables. For example, dark matter relic abundance, direct detection, and of course current LHC bounds. And we see that we can have significant cross section for at the future linear collider for both these chargino or Slepton co-annihilation cases. And the similar thing can be done for the production if we look for the production of muons for both the cases. But one important thing is that if our study shows that the dark matter direct detection and ILC1 TeV plays a complementary role between themselves. So here in this plot, we show that the independent direct detection cross section for the chargino co-annihilation case. Of course, here we are showing all the allowed points by muon G-2, but the relic abundance, we only use the upper limit from that. And the direct detection, we are considering xenon quantum. With the updated LZ limit, there must be another constraint from in that region. So I'm showing the projected LZ or xenon enton limit here. And these red points, these will give the correct relic abundance. But what we can see is that there is ample parameter space available in case of chargino co-annihilation as well, which satisfies the direct detection constraint, current direct detection constraint, but lies well below the neutrino floor or even below the projected xenon enton limit. So that will be difficult to probe. This kind of parameter space will be difficult to probe at the future direct detection as well. In that case, the future ILC can be useful, and we see that if we try to, we calculated the production cross section for the neutralino with photon or the charginos, and these points, these blue points are points below xenon enton or LZ, and the open and close are the xenon enton LZ or below neutrino floors. And we see that we can get around 100 fem to 1 inverse cross section in this kind of mass range for the charge annihilation will be a feasible region. So even if we have, I mean, okay, so if we want to completely discard the possibility of this kind of scenario, we should better look for both of these experiments in the future. The same can be told for this lepton coordination case as well. So here we see there are ample parameter space available below the neutrino floor or below the xenon enton, but this can give rise to considerable production cross section at the, of course, future ILC, ILC1 TeV, and then we can, ILC can be motivated in view of these things that we can, this G-2 and all this kind of direct detection. This can set target for ILC as well, to what to look for, where to look for. Finally, so we are trying to show the future prospects for the electroweak MSSM, but in particular where the NLSP is a charge geno. So this plot, except these points, this is given by the European Strategy Group, and they have given the future projection for various future colliders. For example, high luminosity LHC at 14 TeV, this is CMS and Atlas, and high energy LHC at 27 TeV. And they have even included the FCC HH mono Z limit on the mass gap, NLSP LSP mass gap with the NLSP mass. However, I have been told by expert that we should not take this monojet limit at its face value given in this projected report. It may vary or it may change, it may go well below this limit. So what we have tried to show that also they have shown the projected limit for the linear collider or the lepton collider. So this is for ILC 500 or ILC 1 TeV is the gray line here. And there are again other CLIC result. And now we have just overlaid our scan parameter space available after imposing all the current constraint coming from LHC, dark matter relic abundance. So here we are only considering the underabundance. So the dark matter, the neutralino dark matter can only contribute to a fraction of the total relic abundance. So here we are considering the Bino-Vino case, the Higgsino case, and the Vino case, as it is evident from the mass gap that for the Bino-Vino case, we have larger mass gap, and for the Vino, we have the smallest one. So although we see that for the Vino case, it is kind of impossible to probe this kind of parameter space by even by future high energy LHC or high luminosity LHC with 3 autobahn inverse luminosity. But if we motivate, if we advocate the linear collider, future linear collider, then we can conclusively probe even the Vino scenario. So initially the ILC was motivated or was told as a Higgsino factory, but it can even be a Vino factory. For the Higgsino as well, so one thing I should also mention that this projected report is only meant to be for the Higgsino kind of scenario. But if we consider Bino-Vino or Vino co-annihilation, so the production cross-section might be a little larger than Higgsino, but that can be included in the assumption, or but still we can say that ILC1 TeV can be very important or conclusive in this kind of compressed spectrum searches. So I think I'm early on time. So my conclusion is that, yeah, of course, we haven't found or we haven't seen any signature of MSSM particles, but so of course we know that it is possible that we can constrain the MSSM parameter space with help of various indirect as well as direct limits. But we can to conclusively say something, and if we consider the G-2 constraint quite important, and then we see that together the dark matter and muon G-2 constraint can put an effective upper limit on this kind of electroweak SUSY and LSP, and it can put it can set target for our future search prospect at the Future Collider. And of course, one thing we should also keep in mind that while citing the experimental limits on this kind of SUSY spectrum, it's better maybe we should take a recasting of our analysis, a model-dependent recasting, and then we can see what kind of, what is the exact bound coming from the current searches. So thank you very much for listening.
Questions?
Very nice talk.
Thank you.
Congratulations. Let me ask you a question. You know, you use the value of the G-2 for the standard model, which is in that 2021, I think, review, and now there's more and more indications that that probably the value is higher. So suppose that the discrepancy remains, but at the level of 2, 3 sigma, something like that. Would your conclusion, in particular, the last line of your conclusion that ILC would complete the search, would that stand, or will that evaporate?
Yeah. Of course. So the limit that we are showing is considering the current central value of the discrepancy and then taking the 2 sigma. So if the discrepancy lower, then of course the upper limit will be much lower on the particle masses. And in that case, it will be more evident or more conclusive by ILC to probe. So now the upper limit on these particles from this current experimental limits or the current discrepancy, it's around 700 GeV or so. So for example, instead of taking 2 sigma, if we take 1 sigma, then the current bound will reduce from 700 GeV to, let's say, 600 GeV or something. No? Okay.
So when you talk about underabundant scenarios, can you give an idea how underabundant you are?
Yes.
Is there some plot where you can give values of psi over the parameter range?
I haven't. Yes. So here we.
Yeah. This plot has it. Yes, I missed this. Okay. So you're
of
not
course
desperately underabundant. Okay.
In this region, no, but yeah, maybe the points which are below neutrino floor, those.
No, since this is a linear scale, this is not too bad. Okay. And you don't have too many of the black points. So.
No, not too many.
No, I missed this plot. Okay, thanks.
Yes.
Yeah. Any other questions?
Or no?
Just a curiosity, like, so you mentioned these stopped tracks. So at LHC.
Sorry, what?
Stopped tracks at LHC.
Disappearing, yes.
So which experiments are you talking about?
CMS.
CMS. Okay. So my question was like, I remember that at one point you could do this at the medal detector. Like they had very good resolution for stop tracks. I mean, medal at LHC. So if there was sufficient DEDX, and these particles that you showed, they are quite heavy, right? Order TeV-ish. So, huh?
Yes, order TVS.
Yeah. So maybe medal will also see these stop track signatures, and that has very low background, I think. So,
okay.
But these are not from that, right?
No, I am using just the
CMS.
current constraint that is given by CMS on the lifetime of this kind of particles which are giving the disappearing tracks.
Okay. It's
so
okay. We can talk later. Yeah.
I am not analyzed. I have not analyzed anything.
I see. Okay.